How do we measure the angle and magnitude of a transfer function? So first of all, let's just look at what a transfer function looks like on the j omega axis and the real axis, so in the imaginary plane. So we have some transfer function here, g of s is s plus a. So we can actually write that there's a 0 at minus a. So let's say that I have some point s1, and I'd like to find out what the angle is. So we'll be able to calculate the magnitude and the angle of g at s1. So if we choose s1 equal to minus sigma 1 plus j omega 1, substituting s1 into g, I get that my value is minus sigma 1 plus a plus j omega 1. So to calculate the angle g of s1, I just evaluate what would be the angle of the imaginary over the real part. So this is just like when you calculate the magnitude and phase of an imaginary number. So we're just looking at what is the phase of this imaginary value. So this is fairly easy to calculate. And so I can actually, on my pole 0 plot, I can just plot the value minus sigma 1 j omega 1. And so what I'm going to show here is that we can measure the angle of this transfer function to another point by using the 0 instead of by using the origin and actually substituting in the value s1 into the transfer function. So this is the point s1. We can also indicate where is the point a minus sigma 1, right? So that's the point, that's the real part of g of s1. So that actually shows up here. It's in the right-hand plane, but that's okay. And so we have an angle, if we want to think of it, of the vector that's formed between the 0, that's at minus a, and the point s1. And there's a similar angle that's formed by the origin to the point s1 plus a, right? Because that's the actual value, g of s1 is s1 plus a. So that's this point a plus minus sigma 1 plus j omega 1. So you can actually show that these two angles are the same. So the first point here is positive a, and the second point is a minus the real part, minus sigma 1. And of course the height will be the same, j omega 1. So these two angles are the same, and we can actually show that they are here. So we can calculate the angle alpha as the inverse tangent of omega 1, because that's the height of that triangle, divided by a minus sigma 1. So that's the distance from the origin to the real part of that point, a minus sigma 1. So we can also look at the angle 1. It's the inverse, again, tan inverse of omega 1, which is the height of that triangle, over minus sigma 1, so that's the base of the triangle, right here at the corner. That's this point right here. And then we subtract away the distance to minus a. So we subtract away minus a in order to get that point. So then we see that for the angle 1, we get tan inverse of omega 1 over a minus sigma 1. So these two angles are equivalent. Let's check and see if it's the same for poles. So now we have 1 over s plus a. So if we choose again s1 is equal to minus sigma 1 plus j omega 1, we indicate our pole as minus a, and we can evaluate g of s minus 1. So we'll substitute in minus sigma 1 for the s plus j omega 1, and so then we get a 1 over the real part, which is minus sigma 1 plus a, plus the imaginary part, j omega 1. So to evaluate this angle, again, if you have an angle, a phasor in the bottom, then to calculate the angle of the top over the bottom, you subtract away the angle of the bottom. So our angle of g of s1 will be 0 because the phase at the top is just a real value, so it has phase 0. And then we subtract away the inverse tangent of omega 1 over a minus sigma 1. So we can do the same thing that we did before. I'm going to indicate where s1 is on the plot. And then I'm going to write where a minus sigma 1 plus j omega 1 is. So it's at a similar place, offset by a from minus sigma 1. So again, we can show that the angle 1 is equal to the angle alpha. And we can do that by just looking at the triangles. One of these origins is going to go from, or one of these triangles is going to be formed at the origin and go to the evaluated value g of s1. And the other will be formed at the pole and go to the point S1 as it's just written in the sigma j omega plane. Okay, so here's a more complicated example. Let's say that I have s plus 1 over s plus 2 times s squared plus 4. So this is a fairly complicated transfer function. I'm going to actually calculate the angles of this system using the direct method where I'm just going to add the point S1 to the plot and then calculate the relative angles from that point. So we have 4 total objects of interest here. We have the pole P1 at minus 2, P2, 3 at plus or minus J2. So those are the 3 poles. I'll back this up a little bit so we can see it a little bit better. And then we also have a 0 at minus 1. So I've indicated those values here. Here's the 0. Here's the pole at P1 equals minus 2. And then we have a pair of conjugate poles, one here and one here, which are at plus or minus J2. So I'm going to let S1 be an actual value to make it easier to calculate. So that S1 value is at minus 1.5 plus J1. So that's where this little blue dot is here. And now we can write a bunch of angles, angle 1, angle 2, angle 3, and angle 4. So let's go through these one by one and show exactly what they do. So angle 1 is the angle from the real axis to the point S1 through, based on, at the origin, the 0. So we're going to start here, and we're going to turn our angle till we actually hit the vector that points from our 0 to this point S1. So that's the angle 1. The angle 2, and again it doesn't matter exactly which numbers you choose, you just have to remember which numbers are in the top and the bottom. So for angle 2, again we form a line that's parallel to the real axis, and then we make a vector that goes from the pole to the 0, or to the point S1, and now we're going to calculate this angle, angle 2. And we do the same thing for angle 3. So angle 3 is going to be greater than 180 degrees here because the pole here at plus J2 is above the value of S1. So we're going to have a greater than 180 degrees. And for pole S4, you can see that we have angle 4 over here. So now that we have these values, we can actually write one by one what the values are of the angles. And so the angle 1 is going to be 90 degrees plus the inverse tangent of 0.5 over 1. So how did we come up with this value? Well, I'm going to sort of zoom in on this triangle here. So we have a 0 here at minus 1, and our point S1 is up here. And so we're going to want to find out what is this angle here by first calculating this angle and then calculating the remaining angle. So the first angle that we calculate is 90 degrees. And the second angle that we calculate is the inverse tangent of 0.5, which is the difference between minus 1.5 and minus 1, and a height of J1. So remember, tangent is opposite over adjacent. So the opposite is 0.5 and the adjacent is 1. So that's how we calculate angle 1. Let's calculate angle 2 now. So it's actually quite similar, we just have slightly different values. So for angle 2, we calculate 90 degrees, which is the first part of the angle here. And then we're going to form, again, a triangle based on this length here and this height here. For angle 3, 180 degrees plus the inverse tangent of 1 over 1.5. So it's easy for me to say this. It's more important for you to be able to understand why it is that angle 3 has this 180 point here. So let's look at this carefully. So if we, again, zoom in on this value, I've basically taken this angle 3 up into in this region and tried to show it closer over to the bottom right. So we have a difference in height from J1 to J2 of distance J1, right? So we're higher by 1 on the imaginary axis. And we're further to the left by 1.5 because the real value is minus 1.5 and our pole's originally on the j omega axis. And so we can go ahead and take the 180 degrees that we get from the horizontal line here, so we're going to add this 180 degrees right here, to whatever this angle turns out to be right here in between the horizon and this vector that goes from our pole directly to the point S1. And so again, our height is J1, so that's the opposite part, and then the adjacent part is 1.5, so that goes right here. And so now we can calculate the angle 3. So similarly, we can calculate angle 4, but this one's a little bit easier. So here we can just directly take the triangle 1 because we're 1 higher, and 0.5 because we're to the left by 0.5. So the total angle of G of S will be the angle 1, because it's on the top, it's a 0, minus all the angles on the bottom. So angle 2, angle 3, and angle 4, because those are the angles that belong to the poles. Okay, so I've just repeated those calculations over here. Now I want to verify that it's correct and calculate all the values. So for the first value, 90 degrees plus 26.57 degrees gives us about 116.56. 90 degrees plus 26.57, because 0.5 over the 1 is the same as 1.5 over 3. Those ratios are the same, and so those tangent values come out to be the same, or arctan values. The arctan of 1 over 1.5 turns out to be 33.69 degrees. So angle 3, because we're adding 180, remember, is 213.69. And then angle 4, we can just directly take the arctan of 2, and that turns out to be 63.43 degrees. So with these values, now we can actually do the subtraction to find out the value, the angle of G at minus 1.5 plus J1. And after we subtract these values off, these two are going to cancel. And so we get minus 277.125. I prefer to have these values all the way in between minus 180 and 180 degrees. So this turns out to be 82.875 degrees. So you can verify this by directly plugging in the value minus 1.5 plus J1 into your calculator and solving G of S and confirming that you get the same angle.